Thank you for joining us today. Unplanned psychiatric readmission represent a major challenge for patients, families, and healthcare systems. Individuals with mood and psychotic disorders face some of the highest 30-day readmission rates, driving poor outcome and higher cost. Yet, identifying those most at risk remains remarkably difficult. Advances in natural language processing-based machine learning offer a promising path forward. By applying these computational approaches to electronic health records, we can develop robust, scalable algorithms for readmission risk prediction. This symposium brings together three complementary perspectives on this emerging science, focusing on structured and unstructured EHR data and the large language model. Let me introduce our speakers. My co-chair, Dr. Timothy Miller, Associate Professor at Boston Children's Hospital Machine Learning for Medical Language Lab, will open with an overview of our NIH-funded project. Dr. Miller will then present the second talk on behalf of Dr. Boyu Ren from McLean Hospital, who is unable to attend due to the early arrival of a newborn child. This presentation examines cross-site model generalizability across hospital systems. Finally, Dr. WonJin Yoon from Boston Children's Hospital will present work on aspect-oriented summarization using large language models to extract clinically meaningful information from discharge summaries. We will have 10 minutes for Q&A and discussion on ongoing analysis and future directions, particularly how we might implement these prediction models in clinical settings to assist clinicians in decision-making in the future. Let's begin with Dr. Miller.
Hello, everybody. I will share my slides. And, whoops. Okay, does that look all right to everybody? Okay, thanks, Rachel. Okay, I'm really happy to be here talking with you all and hoping we get some interesting discussion going at the end. And thanks, May, for the introduction, and thanks to everybody who's hosting and putting together this symposium. I'm really excited for it. So the first part of the talk today is going to be some project background. I think I'll just jump right in. So our project is modeling temporality with natural language processing to predict readmission risk of patients with psychosis. So this is a NIMH-funded R01 that's Dr. Hall and I are co-PIs on. And the goal is to predict readmission of patients being discharged with psychosis or major mood disorders. And so this project came together as a very nice synergy of our respective research areas, because Dr. Hall has been working on factors related to readmission risk for a long time. And my group and my colleagues and with my mentors at Boston Children's Hospital, we've been working on modeling temporality in electronic health record texts for over a decade. And so we happened to run into each other at some meetings and realized that we had some shared interests. And it was a very natural fit where Dr. Hall thought, oh, I think, actually temporality, that sounds like it might be useful for readmission risk. And I was really interested in having my lab work on mental health and psychiatric related data. So it was a really nice, sort of serendipitous moment that we got to meet and started planning this project over the course of several years and got it funded by the NIMH in 2022. So the data we have for this project is patients from 4 MGB hospitals. So this is McLean, MGH, Brigham and Women's, and Faulkner, who are admitted for mood disorder or psychosis. So we can look at, maybe we'll get in the next talk, we'll get a little bit more into how we do the sort of queries. but we're going to look for patients who have basically psychiatric admissions, and then with specific billing codes. And then we're going to look at the main data source we're going to look at is discharge summaries for all admissions. We do have progress notes for some patients, but we don't have progress notes for every site equally. So we kind of focus on discharge summaries as the sort of lingua franca. And then for almost all sites, we have pretty similar structure data. And that's one of the real nice benefits of having this. It's 4 sites, but they're all within the MGB sort of umbrella. So the database is the same structure. So that gives us sort of a clean experiment, even though the patient populations are different. And then our target is all-cause readmission. We can talk a little bit about that if people have questions, why we chose all-cause readmission. But the long and short of it is all-cause is much easier to extract from a database record. And if you have a patient with a significant history of mental illness, has multiple inpatient stays in their past, and they get admitted in the future, they'll typically have a billing code that represents their mental illness, whether it's a mood disorder or psychosis. And so it's hard to extricate, whether a disorder is, or whether an admission is like because of psychiatric or if it's because of something else. Whereas for our sort of base of, what are our prediction instances when we're predicting discharge from a psychiatric inpatient stay, it's a little easier because we can limit that to psychiatric floors in our 4 sites. So there's a little bit of an asymmetry there, but we think all-cause readmission is a useful target because of the patient's history probably is relevant to most admissions, even if it's not purely a psychiatric readmission. So our hypothesis with this project is that if you explicitly model the timeline of the patient's history, medical history, that will have signal that we can use to make more accurate predictions. So there's a version of this study you can imagine where you just sort of dump, and especially in the LLM era, you can imagine this. You just dump all the text into a statistical model and ask it to give me a yes/no prediction, and sort of don't worry about what's going on in the middle, the sort of black box of the giant neural network model. But we had this thought that if we, especially when we wrote the grant in the pre-LLM era, that representing temporality was going to be hard for even large black box models. And so what we should do is sort of build models that sort of explicitly target the intermediate step of understanding the temporal sequence of what happened with that patient, and then try to use that as a classification input. So the activities that we've done for this project so far, ongoing work, we've extracted a data set of McLean discharge summaries. We've created a manual labeling schema for how we're going to mark up the temporal events and times, basically the patient timelines for this data set. We've developed new machine learning models to do temporal information extraction. We're not going to present on that today because that's under review. We have some manuscripts that are out and under review, but we don't want to report on that quite yet. We have some really exciting stuff to report on before we get to that. And then we've been extracting temporal information. This is going on right now, classifying these representations for readmission risk. And then we're also doing a study where we're comparing against human performance, where we have clinicians who are reading our cases and sort of using their knowledge and to make predictions about what will happen. And we're going to compare that to machine performance. So I just want to give you a little bit of background on what our temporal model looks like for the sort of what we put into the grant, how we think temporality looks. And so here's an example from a sort of general medical example. She was admitted for an appendectomy on January 12th. She had a rash after surgery, which was successfully treated with hydrocortisone on the 18th. So this is, I think, a very typical type of sentence you might see in an electronic health record, narrative clinical note. And we have things that we call events, which I indicate in blue here. These are just things that you could put on a timeline. So the word admitted, appendectomy, the word surgery, which refers to the appendectomy, the word treated, and then the word hydrocortisone. And then we also have time expressions, so January 12th, and then the shortened mention of the 18th, which, as a human being, you can sort of make this inference that this is January 18th of the same year. And so the first part of the task is just, can we find the events, the things that happen to the patient that we would want to have on a timeline? It's extracting the blue things. And then the second part of the task is, can we find the time expressions? Because these are going to sort of act like anchors on the timeline. Where do we connect these events to? So, there's these two time expressions are the same type. They're both sort of date, but there's other types of time expressions like times, sets. There's one we call pre-post X, which is things that are pre and post op sort of terms. There's multiple different types of time expressions. And then the really, really crucial part is temporal length. And this is also the hardest part, both for humans and for machines. We want to take all these events and relate them both to each other. So we get a sort of relative sequencing of events, and then also connect them to dates and times so that we have sort of an absolute anchoring of events. So in this case, some of the example links are, we know admitted is before the appendectomy, that the 12th contains the appendectomy. So the appendectomy happened on that date. Treated and hydrocortisone are sort of roughly similar events. So we say that they overlap. We say that the rash begins on the surgery. So that rash was caused by the surgery. So it essentially starts at the same time that the surgery ends. And then we say rash ends on treated. So once it's treated with hydrocortisone, the rash event sort of stops. So that's just sort of an example of how we extract time, and then how do we classify it. So we had this idea that, as I mentioned, this is a really hard task. We're not going to get perfect performance from our models, even if we get really good training data. So our idea was, we're going to take the set of relations and events and time expressions that we extract, and we'll put them into a graph where the nodes in the graph represent events and time expressions. So here we have these blue and yellow circles. And then the relations that we extract represent links, represent edges in the graph. So we have the edges here, like a contains edge between past week and not sleeping well. That represents the fact that temporal expression contains that symptom. So once you get it into this graph format, then we can take advantage of a model type called a graph neural network. And that's sort of the ongoing work that's happening right now. We have some, promising results, but nothing published right now, so we won't be able to share this. But I just wanted to give you a roadmap for where the project is going. And then as you see the progress we've made so far in the next two talks, we'll be able to sort of maybe have it in your mind where we're going and sort of how everything fits together. Okay, so we've made good progress so far. We've had several published papers on sort of our background model and on some other clinical prognostic prediction models using long documents that were sort of laying the groundwork for the sort of psychiatric work. And then these two highlighted in red are the two that we're going to see talks about today. So Boyu Ren's paper was published in JMIR Mental Health, and in there we have a cohort description classification models that I'll talk to you about next. And then WonJin Yoon had a paper at EMNLP. So folks in this call may not be familiar with the EMNLP conference, but it's a top tier AI NLP conference. It's really, really exclusive, low acceptance rate conference. So that we're really proud to have this sort of methods paper about how to handle psychiatric data published in that conference. And WonJin was able to go to that conference a couple of weeks ago and talk to a lot of people about this work. So that was exciting. We have other manuscripts under review. A paper, so data annotation, that's basically talking about how we created the labeled data set of temporal information on the discharge summaries. That's at a conference called LREC, which is a NLP conference for creating labeled data sets basically on text. And then temporal information extraction paper. This is a work describing how we do the information extraction, how we pull out the events, time X's and T links, the links, and that is at a conference called AMIA Summit, which is a medical informatics conference. And then work in progress, I mentioned the human expert study. We're doing we're collecting data right now, and then predicting readmission with temporal graphs. So that work is also ongoing, where we're sort of training our models and getting results. Okay, and with that ends the first part of my talk, and I was going to hand it over to Boyu, but his baby apparently did not get the Outlook calendar invite and decided to show up early. So I will move right on to presenting his work for him. So sorry to miss Boyu today. We're happy for him. And I want to thank him for putting together these slides. And I will sort of do my best to get through them. And oh, I see it. It paused. So I think I might have to reshare. I switched tabs here. Okay, can anyone give me a thumbs up if that looks right? It's the same same front slide as before, but okay. I think everybody's seen it. Okay, so as May mentioned, we're interested in 30-day unplanned readmissions as a key quality metric for care. We think it's important because this work is important because a lot of models have only been validated within a single hospital. So there is some published work on readmission prediction, actually not that much, but the work that is out there is usually validated on a single hospital. It's not totally clear, if you see a paper like this, sometimes they'll say, oh, we built a risk prediction model and publish it in a journal, and then everyone reads the paper and says, okay, so these are the things that predict risk. And it's not as simple as that because and that's the question we wanted to ask, because we have 4 different sites and we have similar variables for all of them. So we could sort of run the experiment and figure out, okay, let's run it at McLean, and then we'll see whether those variables are true, the things that we find about the variables at McLean, whether they're also true at MGH. So there's not very much evidence on that, and we wanted to create that evidence base. So the goal of this work is to explicitly evaluate cross-site prediction performance of readmission. So we have standardized data set using the structured data from the electronic health record. So in this work, we're not going to be using the text data yet. We're just going to be using the structured data. And the sort of setup of the experiments is we're going to train on one hospital, and then we're going to test on all of the hospitals. So we have, if you have 4 hospitals, that means we'll train on one of them, and then we'll test on all 4. So one of those tests is a sort of in-domain test, and the other 3 are out-of-domain tests. And then we can do that across all 4, where we use each one as a training set in sequence. And we also benchmarked multiple algorithms, including sort of straightforward linear models, logistic regression-based model, and then some nonlinear models that allow us to get some interaction terms, random forest. So we'll talk a little bit about that. The data set, we have 4 hospitals, McLean, MGH, Brigham and Women's, and Faulkner, and we looked at admissions for mood disorder or psychosis. So the included criteria was, for mood disorders, we use billing codes ICD-10, F30 to 39. For ICD-9, we did have a mapping into this space. Or we use psychotic disorders, which is ICD-10, F20, F2, star. We focused on patients that were ages 18 to 65 years old, because younger than that and older than that, there are sort of different etiologies related to the diagnoses we're interested in. And to consider something a psych-related encounter for the sort of being a classification instance that we're going to try to make a prediction on, we used the structured variable inpatient, outpatient, it's called, and we limited to where it's labeled as inpatient. And we looked at whether it's at McLean Hospital or whether it's on one of the psych floors of the other hospitals. So we were able to do some quality checks to show that that was pretty high quality. I would say it has pretty good PPV, but it doesn't have 100% sensitivity, because we know that there's probably admissions that you might consider a psych-related admission that are on other floors, but to have the sort of purest data set we could get that we know these are almost all psych-related admissions, we limited it in this way. And then our dependent variable was all-cause readmission within 30 days for reasons I explained in the last slide. And so we ended up with 52,000 some classification instances across 4 sites, with McLean being the largest and MGH being the next largest, and Brigham and Faulkner being quite a bit smaller. So the predictive variables we used are age of discharge, sex as recorded in the electronic health record, race as recorded. These are not perfect variables. If you're designing a system from scratch on what sort of variables you might want to use, you would probably model these differently than how they are in an electronic health record. But we did the best we could with what we had here. And then we looked at diagnosis codes for the current encounter, obviously psychosis and mood disorder. And we include these because, probably all of you are aware that these are diagnosis codes that are often overlapping and sort of diagnoses that aren't totally, they're not independent or orthogonal. There's many patients with both. We also looked at anxiety related codes, which is a different sort of section of the coding space, but it's also, we thought, might be relevant. And then we looked at substance use disorder related billing codes, because we thought that's also, I think it's pretty widely hypothesized, at least, that would be a predictive factor. And then another variable we looked at, which we were able to extract pretty easily from structured data, was length of stay of current encounter. So we know when they were admitted in the current encounter and what the discharge date is, so we can show. And that's just meant to be a proxy for how severe was the sort of illness that caused the current admission. And to get in a little bit of the modeling procedures, we had logistic regression and random forest models. We split the data 3 to 1 into a training and testing split. this I sort of have gone over, but for insight, we do insight or in domain, we say, it's a little ambiguous when I say insight. It sounds like I'm saying one word, but with insight maybe is a better way to phrase it. You're testing on the same hospital, and cross-site is testing on a different hospital. So we're going to show all those results. And then for the metrics, we have an area under the RLC curve. This is kind of a sort of a single variable that represents, if you're not familiar with this metric, it just represents the sort of amount of signal that you're capturing, regardless of sort of where you put the cutoff point for your classification model. And F1 score is a sort of snapshot at decision boundary of probability 0.5, where you assume everybody with higher probability than 0.5 is classified as true for likely to admit, and everybody below that is classified as false. So here I'm first going to show you a table of sort of demographic statistics, and this is a lot of numbers. I wanted to give you the whole table in case there's anything you are specifically interested in, but I'll just highlight a few things that are circled here. So one is that the racial demographics between these sites are quite different. Brigham and Women's and Faulkner have around 60% white population, and whereas McLean and MGH have around 80% white population. So that's a pretty significant difference in what the patient demographics look like, especially given that they're in the same city. And then the billing codes, we also see different demographics of primary billing codes. So the psychosis, for example, is 20% at Brigham and 38% at Faulkner. That's a pretty significant difference. And then at the bottom here, we have highlighted this is the outcome. So this, you can think of this as basically the prevalence of readmission. And this varies quite a bit too across sites, where we have a high of 43 at MGH and a low of 21 at Faulkner. So already going in, we know that our populations look different among some, sort of obvious variables that you might look at. And then next I'll get to within site results. And so these are the results of the logistic regression. You can see the coefficients here, or sorry, the odds ratios here, and the p-values. And the thing to point out here again is, this is too many numbers to sort of take in at a glance, but the thing is, we would like to point out is, something like length of stay, which we think is a sort of obvious predictor of, the longer the stay, maybe the more sick they are, maybe the more likely they are to readmit. But in fact, while this variable is significant at multiple sites, it doesn't even always have the same sort of direction. So that tells you already that, this kind of answers one of the original motivating questions is like, do the variables work the same way at different sites? And it's pretty clear from here that they don't. And then random forest, this is sort of a way of looking at feature importance. And then we can sort of see the decrease in accuracy when removing the variable. And here again, the main thing we're trying to highlight is the difference in across sites. So for example, looking at legal sex, it makes some amount of difference at MGH, but it moves in the opposite direction at Brigham and Women's. Length of stay does have pretty high change in performance when you remove it. So that means, at least at MGH, that's a very, very important feature. Yeah, so there's too many numbers to sort of get into detail here with all we want to show you today. But the main slides here are the primary results on how good of a performance can we get. So this is going to show you, I'm going to focus you on the upper left here, because this is going to be the AUC, which I think is probably the most revealing metric. And then this upper left one is the logistic regression. So we've left off any performance metric here that's under 0.6. So what you can see is that most of the yellow is on the diagonal, and these are the within site classifications. And then off diagonals, we have a lot of whites, and white means basically there's no signal. Pink means there's actually inverted signal, which I take to mean basically it's just noise. So extremely light yellow colors mean we're not giving much signal above the sort of noise level of the classifier. So the random forest on the bottom left here does perform a little bit better, and especially it does show a little bit of decent cross-site performance when it is tested at MGH. So multiple models trained at other sites can perform well at MGH, which I think is, the sort of, I don't want to get too much into interpreting that. The next step we took was basically accounting for covariate shift, and this is just a statistical phenomenon where, as we know, the input predictors have a different distribution at the different sites. So the different amounts of patients identifying as white and black, different amounts of patients, different prevalences of patients with psychosis versus not having a psychosis code. So Boyu implemented this method called inverse probability weighting, which helps us sort of reweight our training data so that it looks like the data you're going to test it on. So for example, if your test hospital has a higher male population than your female population, sorry, I'm saying that backwards. If the test site or target site has a larger proportion of females than the source site, then you might want to upweight the female subjects while you're doing the training so that the model sees data that looks like your test site data, right? And so we implemented this and retested, and you can see we just basically tested the off-diagonal elements here. This is the cross-site evaluation, and in the upper left here, you see a lot of numbers below 0.5. So basically, what that's telling you is that that method didn't work. What that tells us is covariate shift was not the problem, right? It wasn't just the distribution of the input variables that changes. It's something really more subtle than that. The relationship of the variables to the label we're trying to predict is actually changing. And that just means, they're seeing different types of patients, even if the patients have the same sort of demographic factors, there's sort of different types of patients. So in conclusion here, I'm going to wrap up to get to WonJin. The readmission prediction, we found it's hard. I think everybody knew it was hard. Published work has also, numbers that are in the same ballpark. The structured variables account for a pretty small amount of signal, like 0.5 AURC would be no signal at all. 1 would be, perfect signal. We're getting something around 0.6, showing that we're finding some signal, but not a ton. The cross-site prediction is really hard. So the variability is not explained just by differences in the distributions of the input variables. We need more here to be able to do this. The differences in sites, I think some of the experts on this symposium and our collaborators will be better able to sort of explain what the differences in populations are at these different sites. But there's a lot of differences in the settings that might cause different relations between the predictors and the outcome. We think of this work as providing a baseline for assessing generalizability of readmission prediction models going forward. We know that you're going to need better variables, better input variables to be able to predict this with any sort of increased amount of signal. And we think, as we came up with the project, we definitely were thinking about text the whole time. So, this is a good transition where how do we move from this, structured variables only to thinking about like, how do we extract information from the text? And with that, I will wrap and queue up WonJin Yoon.
Good morning, everyone. Does everyone can see my screen? Yep. So good morning, everyone. My name is WonJin Yoon, and I'm a postdoc at Boston Children's Hospital and Harvard Medical School. So today's talk is about using large language models for psychiatric short-term readmission prediction. And by language model here means it encompasses large language models and also pre-large language model era method like transformer-based language model, fine-tuning of them. So this is a slightly more method paper, and this is from EMLAP 2025 paper, but it's modified for our talk. So I'm going to start with introducing the task at a glance. So it's in connection with the previous talk. So it has the same output objective, the prediction of binary prediction of 30 days readmission task, but the input data is slightly different. So this is a natural language processing work, and our input is clinical documents. It's a psychiatric notes, and the unit of input is 1 discharge note per admission. So per admission, we are trying to predict the 30-day readmission. So so the easiest way, or more maybe the straightforward way of predicting this would be a zero-shot LLM approach. But there's we have tried it first, but it didn't show really great performance at the first try. And another way would be the training of transformer-based language models, such as fine-tuning of the language models. And we're going to also talk about it in the coming slides. So now we know the task definition. I'm going to introduce the obstacles of this task setting. So because we are using discharge note, and discharge notes are usually very long, it's about 8,000 tokens, and in the words, if we count unit as words, it's about 4,000 words. more in other translation, it can be about a 10-page length of a document. This is pretty lengthy in our NLP world because the previously like language models usually can handle up to 500 tokens. And nowadays we have more large language models, but they also have the same problem of the second point. So the second, I'm going to move on to the second point is that when we use language models or this deep learning approach, memory requirements for language models grow quadratically with input length. So this imposes practical constraints on computational resources. And because this is a highly sensitive data, commercial clouds are not a viable option or feasible option for us, as this is very sensitive data. We cannot move outside of the secure firewall, so that's not an option. So this gives us to try out approach we call summarize, then classify. And we are trying to use large language model for the first step, the summarization part. And then we can try out some more accurate approaches like fine-tuning with that summaries. So now we are moving on to motivation, and this is slightly more technical part, but not like very technical. So we all know that when we type prompt or question to large language models like ChatGPT, if we type slightly different question or prompt, then they output different results. So it also applies to the summarization with large language models. So if we change prompt, then they will generate a different summary. However, we do not know which output is optimal, which output has the best summary. And another question related to this is that if we have two different output or two different summary, are they really different in content, or are they just merely a paraphrased or reformatted variation that we don't need to, if we have one summary, we don't need another summary for to get the information. This is very important for our task, especially because we are trying to compress 10-page documents into a half page or less, one paragraph output. That's a summary. And we wanted to make multiple summaries to complement each other because there will be definitely some of the information missed during this like summarization step because it's 10-page to 5 half-page paragraph. So the question from this slide is that do the language models, do they encode different information if we try with different prompt? So here's the simple example that we tried before we designed the entire like experimental design. So this figure shows the comparison of true positive predictions from models that is fine-tuned on different summary types. So we try to summarize with 3 different prompts, and then we give the exact same discharge note with a plain and risk factor focused prompt and timeline focused prompt, which I will show an example later. And then we make 3 summaries, and we iterate it for the entire data set. And we have 3 summary data sets, like plain summary data set, risk factor summary data set, and timelines summary data set. And we have trained a transformer-based model, like BERT model, but specialized in medical domain, PubMed BERT. And then we look at the results. So the area, the 66, you can see here that this pointer points. This is the area where samples correctly predicted by the model trained with this plain summary dataset. But these 66 samples were missed by the models that trained with other type of summaries, which means that these three type of summary data sets might have different information that the model can extract and learn from it. This is just a one simple experiment, so this doesn't not guarantee this the statement I just said. So we scaled it up to the more statistically reasonable way. But this slide serves as a motivation of this study. So in summary of this motivation, we're going to see how could we check the output of the LLMs. They really have different information or differences if we use different prompts. And another question is, can we utilize this different information differences and then utilize them for a better model, the model that can predict better on this task. And I just wanted to make a note that this is not about the quality of text generation evaluation. Like some of us might familiar with some metric like Luge or bot score, but this is not about those kind of approach. It's more about measuring the informational differences. So I'm going to move on to this data processing pipeline, how we did it. So we selected the records with some criteria from hospital databases. And then we get a full-length notes, which I mean about discharge notes that's having about 10-page or more length. And then we try to summarize it with large language models, but we apply 3 different prompts. The first one is plain summary. The second one, we tried risk factor focused on summary. And then the third one is timeline-based summary, which is in connection with the previous presentations as well. So the plain summary, it's just a really plain prompt. We just ask LLM to summarize it. And then the more interesting part is this prompt 2 and 3. By using this method, there's some side benefit of this method that we can utilize some experts' input. We can ask someone like May to the question, what is the important factor if you are trying to decide whether the person will be readmitted? And then the experts can extract some risk factors or some inputs from their own experience. And then we can smoothly integrate those experts' knowledge into this pipeline without doing any excessive feature extraction steps or some other way. This is more natural way, we might say. So this is one of the example of the prompt. The first one, I'm going to show the timeline focused one. And as you may see on the previous presentations, we are extracting some of the data of the event and what is the event. So we give large language model this kind of instruction, and then we ask language model to extract the output format like date and then event description. And by doing that, the language model will generate timeline focused summary, and then we can make a data set out of this prompt and large language model. And so we have 3 data sets generated by these 3 different prompts. So here comes a little bit more deeper into a paper method part. So this paper has 2 research questions. The first one is maybe more interesting to NLP researchers, but this can be also interesting to other ones as well. But the first question is, does the use of this large language model-based aspect-oriented summarization, which means if we give some prompt and then focus on this kind of aspect, then that's an aspect-oriented summarization. Will it extract a different information signal, and how can you measure it? And is it really different? That's the first question. The second one is that now that we know that if we use different prompt, we have different outputs. And how can we utilize those different information very effectively? That's the second question. So yeah, here comes the first research question related slide. So we are trying to measure the different information signal. And how do we do that? Then we try to compare pairwise similarity scores between the models. So I brought this figure, the Venn diagram from the previous slide. So it's expansion of this idea that we train the models because the models feature extractor in a large sense. So we are trying to use this BERT-based models. It can be any models, but use it to extract the information from the summary. And then we are trying to compare the outputs of two models and then compare the list of outputs and then the list are sorted with the probabilities. And then if we could compare the list of outputs, the order of the predictions using Kendall-Stau distance, then we could maybe we could say that we can compare this output of the information extracted from those outputs. So for example, if we train a model with exact same data set, and if the training is if it does not involve any randomness, let's say, in that case, the output list will be identical, and then the distance will be 0. And if we learn it the entirely different way, for example, the first one is kind of 99% accuracy predictor, and the second one is near 0 predictor, then the output list would be completely different, and then the Kendall-Stau distance will be pretty high. Because we wanted to make it sure that we don't make it we wanted to alleviate the probability of the randomness. So we repeated pairwise similarity scores multiple times, and then we make a control group and experimental group here. So we have trained 10 models using the same plain summarization, risk factor summarization, and timeline summarization. And then we measure the distances between those models' outputs. BERT-based models, they have some randomness based on the random initialization steps. So this is to measure the effect from those random initialization effects, and you can see this distance is from that results, and that's the control group. Experimental group was to compare the outputs from the plain model and the risk model. We also have 10 different each models per each summarization, and then the distance, as you can see here, is higher than the intra dataset experiment when we use inter dataset experiment. So this is the experimental group, and this implies that there's a different information if we use different prompt than if we make a different summarization data set. This is might be a little bit more interesting to the group. So now that we know that there is a signal differences, there's different information. So how can you effectively utilize those 3 different data sets, summary data sets? We experimented 2 methods. The first one is instant concatenation. So it's basically if you open a notepad and then copy paste the 3 different summaries, and then save it. And that constitutes one large summary for our discharge note. And then we iterate it for the entire discharge note. Then we have if we have 100 notes in the raw data set, original data set, then we will have 100 summary data sets, and each summary has 3 different type of summary. So that's what we called instance concatenation, and we just call it merged in the next slide, in the results slide. Another way we try was dataset concatenation. So it's about data level concatenation. And we have 100 summary for plain, 100 summary for risk, and 100 for timeline. And then we just merge it. We just put it in the same folder and use it as a one data set. And then we merge the output when we make a prediction. And then we have prediction for 3 different prediction for one admission. And then after that, we use a soft voting or any voting to merge it. So the second idea has some similarity with the data set augmentation, but actually this is a summary, so it's not creating a artificial synthetic data set. So there's a difference between the augmentation and this approach. So this is our slide on the results. So the first red box is the merged approach, the one we made a slightly lengthier summary with all of them putting in a one notepad. And as you can see, the red box has a better performance than each of the single summary here. The plain summary, risk factor summary, timeline summary shows it like here, but the merged one shows better performance. It's not like always 100% better on this merged data set or this soft voting or any voting, which is the second method we showed. But we have a strong tendency that this soft voting, any voting, or merged approach has better performance than the single summary results. So if anyone is interested, if you could see the paper, there's another a lot of tables that we compare with zero-shot large language model results, which is far less accurate than this approach. And there's another approach like sliding window approach, or the another language model approach. But for the interest of time, I'm gonna conclude the results in here. The final slide is that I'd like to acknowledge our collaborators. Team Miller and MEI-HUA are the MPI of this project, and Gagana Savova is senior instructor in this project. There's me and Boyu Ren, Spencer Thomas, and Chanyu Kim, who was a visitor from Korea University. And the right-hand side, we have clinical collaborators, Rick, Laura, Anna, and Hyunjung from Mass General Brigham Hospital system. So we are researchers from multiple research institute from Boston Children's and Mass General, and most of us are affiliated with Harvard Medical School, and we are funded by this NIMH project. Thank you so much for listening. And here's the paper link. Thank you.
Great. Thank you, WonJin and the team. So if anybody who has questions, please send it to the chat. And we have a few minutes for questions and discussion. Now, before I see any questions, I just want to say that looking ahead, our team is now integrating these complementary approaches, combining cross-site structured data, aspect-oriented text extraction, and temporal modeling. And as Tim has alluded, we've developed a pipeline to automatically extract patient timeline at a scale, capturing not just what clinical information appears, but when events occurred and in what sequence. So in psychiatry, where symptom progression and the recency often matter as much as the presence. So these temporal dimensions may be a key to build models that truly reflect the dynamic trajectories leading to readmission. So we hope to come back next year for the updates. And I don't see any questions. Q&A, yes.
So I see a question from Rich
Yeah.
Fletcher in there. I think that's a really good question. I could take a stab at it, and maybe WonJin can weigh in too. So Rich is saying, I guess instead of using these summaries the 3 different summary types that WonJin mentioned, could we try doing some other type of lossless compression? If translated to another shorthand notation, the token size of 4,000 tokens could be reduced significantly so that it's a little bit easier for an LLM to interpret or for other types of models to interpret. I think that's a great idea, and maybe one version of that is basically just another aspect-oriented prompt, which is like just print out everything in the note that's not filler or note bloat and is not redundant. That's something that LLMs might be able to do pretty good at. I think maybe it might be hard to get down to 500 tokens, but maybe we can get down to 1,000 or 2,000 just by removing pages and pages of pulled in semi-structured data of medication orders that are somewhat redundant with the narrative. But on the other hand, we sort of started doing this as to get around a technical limitation, because at the time, especially with the resources that we had inside the MGB firewall, it was really hard to do any sort of LLM training. Now we have a little bit better resources, and we could do a little bit of LLM fine-tuning if we wanted to. Even I think on full notes, it might take a while to run, but we could technically do it. But in sort of having to meet this constraint, I think we ended up in sort of an interesting place where we have basically a classifier that is features engineered manually by experts who are like, I think this is important. And so a clinician who's works with this data every day and works with these patients every day can say, I think this is important, and write a prompt. And then it's easier than ever to sort of take clinician subject matter expertise and get it into a classifier through this pipeline that we've created. So I think that's a pretty cool way of doing it. I do think we owe it to the field to maybe just show like what happens if you just do like the most simple kind of classifier, and maybe doing something like what you suggested, Rich. Any thoughts on that one, Gene?
I totally agree with what you think, and I think it would be pretty interesting to discover the lossless compressions, but yeah, at the moment we didn't try this kind of compression method at the moment.
The next question is about epic summarization. Unfortunately I don't know very much about that. I don't see the epic. So I certainly don't see the epic front end in my research. I don't know exactly what they're using behind the scenes. But I wonder if that's being stored anywhere, if that's something that potentially could be used in the future as a input to classifiers too, or if it's only generated on the fly. Yeah, Justin says something inside of the Azure, Microsoft, and I think at least I know they have access to OpenAI models inside of Azure, but I'm not sure if that would be my first guess. But that's just a guess.
There's a third question, Scott.
Yeah, given that
You
timeline summaries might
Yes.
have broader clinical utility for clinicians, I wonder if these could be created in real time and then invite clinician confirmation. Yeah, that's an interesting question. Some of the reviewers of WonJin's paper, one of the comments we got was, do we know that these timelines and other summaries don't have hallucinations? And we did some qualitative evaluations of them. May looked at a pretty big snapshot of them to see, and was really impressed with the quality of the summaries. But we didn't do a formal evaluation of counting hallucinations, which I think is something you would really want to do. Like, we're thinking of this as an intermediate step where ultimately the classifier downstream can figure out what information to use and what to discard, and that we wouldn't show the summary to a person. I think if you were going to show these to clinicians, you would definitely need to do some, controlled study first, and then maybe do some sort of clinical studies too. But that's interesting that you think they would be useful. I mean, yeah, that's what sort of motivated the whole temporal information extraction project from the start that my mentor started.
I think our goal is trying to get the model work and then have clinicians' utilities. So we really relies on the clinical fields to give us input and then improve our models and put into the clinical workflow, and that's the goal. But I think our time is up. So thanks to our speakers and the audience for joining us. Thank you so much.
Thank you all. Feel free to contact us later.